Hello. So in this video, we're going to study the concept of second-order stochastic dominance. So first, let's define that. So the definition is that the distribution f1x, it second-order stochastically dominates f2x if and only if a function s1x less than s2x. So we will shortly define this function. And this s function is simply the integral of the CDF of those two distributions. Okay, we'll shortly define that. So this holds for all the x in the support. Also, that we have the same level of those s functions if x equals to b. Okay, so formally this s is defined as the integral from a to x, and it's the integral of the CDF. Okay, so which is the area under the CDF functions. Okay, and in addition, we can say that f2 is a mean preserving spread of f1. Mean preserving spread of f1. Okay. All right. So we can study some basic property for that, for the second order stochastic dominance. So similarly, we'll have an equality here. So the expected utility, okay, for a decision maker here, the integral from a to b, the expected utility given f1x, this is larger than the expected utility given f2x. Okay, so this holds for every concave utility function. Okay, if and only if f1 second order stochastic dominance f2. Okay, so here notice that this ux has to be concave, so this decision maker is actually risk averse. Okay, so we can have a short proof sketch of the proof for that. Okay, so the expected utility, we can expand this by the integration by parts, right? So ux fx dx, and then this is integration by parts. Okay, so it is simply ux fx, this is the CDF after the integral, and this is evaluated from a to b minus the integral from a to b u prime x, this is derivative of ux times the CDF fx dx. Okay, so the first term becomes ub times 1 minus ua times 0. Okay, minus the last term here, the copy and paste. Okay, so this becomes ub minus, okay, so again we use integration by parts again for this term, okay, to expand that. So this becomes u prime x, and what is the integration of fx? So it's sx, right? By definition of the s is simply defined as the integral of the CDF. So that's exactly what we need here. So sx evaluated from a to b plus the integral from a to b u double prime s x sx dx. Okay, right. So this is ub minus, and this term becomes u prime b s b plus copy and paste. Okay, good. So we have this result, then we can take a look at what we need here. Right, we're going to show this inequality. Okay, so that becomes the integral of from a to b ux f1x dx minus the integral from a to b ux f2x dx. And then this is using our result here. So this is simply u prime b, right? Because ub, this is the same for the two terms. It's cancelled. So u prime b times s2b minus s1b plus the integral. Then this is u double prime s times, we write those two s together inside of the integral here, s1x minus s2x dx. Okay, so given the conditions that we know this is negative, right? If we want this way, right? If we want f1 second order stochastically dominates f2, then this is negative. Then because we know that it's concave, right? The utility function is concave, so this is negative. Okay, so overall, this is positive. And we also have that those two, they're equal to each other, so this is 0. So overall, this thing is positive. And then we prove this, okay? And the converse is also true. So this is a brief sketch of the proof for the basic property for the second order stochastic dominance, given that the agent, this decision maker, is risk averse, right? Actually, the utility function is concave, and then this decision maker prefers prefer f1 over f2. Okay. Good. So another thing that we need to show is that something we also mentioned in the definition for the mean preserving spread, right? So here we notice that in this definition here is, we call this f2 is a mean preserving spread of f1. So we can guess that those two distributions, they have the same mean, right? So here we can guarantee that by showing that those two distributions, they have the same mean if those two s functions, they have the same value if x is equal to b. Okay, and so now we can show this as follows. So sb, okay, this is by definition is simply the integral of the CDF function, right? fx dx. So how do we show that, though, if the s functions, they are the same given x equals to b, then the means of the distributions, they're the same. So how do we show that? Simply we use the integration by parts again. Okay, but how do we do that? We just multiply 1 to here, okay, and then we use the integration by parts again. Okay, so that's a very useful tool in those contexts. Okay, so now we can do the integration by parts here. So the first term is fx times x evaluated from a to b minus the integral fx, this is density, times x dx. Then this term is actually the expectation, right? So it's the mean. So the first term becomes fb times b minus fa times a, then minus the second term, the expectation or the mean here. Okay, good. So the first term is b, and this is 0. Then this is simply the expectation, so minus ex. Okay. So what we can observe from this is that if s1b for f1 equals to s2b for f2, then we immediately know that e1x for f1 is equal to e2x for the f2, right? Okay, so we go back to the definition here. We say that in this case, F2 is a mean preserving spread of F1, and this is just a definition for that. Okay, and the reason behind or the justification for that is we just showed that. Okay, it's just as what we have shown above. So here we have the S1b equals to S2b, so that the expectations for the two distributions are the same. Okay. Okay, good. Now we can draw a little picture. Okay, like what we did in the previous episode when we studied the first order stochastic dominance. Okay, so let's do that. The vertical axis is CDF. So the horizontal axis is the random variable x. Okay, let's say our support is from 0. Okay, so A is 0 now. 0 to B, somewhere here. So if x reaches B, then CDF must have a value of 1. Okay, so now we want something for F1, which is stochastically a second order stochastic dominant over F2. Okay, so we can draw something for F1 like this, just a sum line here. F1, okay. So by definition, remember that for all the x between A and B, or 0 to B, here in this case, then what we have is that it's always true that as 1x, which is the integral of the CDF, or the area below the CDF curve, is less than as 2x, okay, for this to be true. So it means that, and also remember that if x reaches the endpoint, goes to B, then we also must have that x1x equals to s2x. Okay, so it means that in the s1x is smaller than s2x is always true. Okay, in between the support until it reaches the x reaches the endpoint B. Okay, then in that case at the endpoint, then the two s functions given the x equals to B, then those s functions, they're the same. They have the same values. Okay, so then we can draw this F2 as a mean preserving spread of F1 as something like this. Okay, this is F2, and we denote those areas between the two distributions as C1 and C2. Okay, so and by this equality here, we know that C1 must be equal to C2. Okay, so that when x reaches the endpoint, then those two s functions, they will have the same areas overall, right? Over areas under their CDF curves. Okay, so this is one possible example of the second order stochastic dominance, right? So intuitively, this is also what we call the mean preserving spread. So the distribution is, for example, for the F1, the distribution for F1 is it's spread to the two sides, right? So here, so F2 has a higher variance. Okay, so the risk averse agent or the risk averse decision maker prefers the F1 over F2. Okay, so in this case, so remember that the areas under F1 is always smaller than F2 if x is in between the support, right? It's is from 0 to B, right? Not including the two boundaries. So, and this is true until the endpoint x equal to B is reached, right? So after that, after when x is equal to B, in this case, then S1x is equal to S2x, right? So in then in this case, then those two the areas or the integrals of those two CDFs now they become the same. Right? Okay, so and we also noticed that because of that, right? Because the of this property, then we can notice that actually if F1 second order stochastically dominant F2, then the F2 has to goes below F1 when they reach the endpoint, right? So it cannot be the other way around. So if F2 is above F1 in this case, then it's not what we are saying that F1 second order stock has a dominant F2, right? So it's the other way around. So this is a very important intuition and something to notice, right? Okay, all right.